By now you know that I really enjoy exploring speculative topics in science, and particularly the scientific probings, the speculation lying on top of the scientific probings of the ever-enticing, unknown territory at the peripheral of our embodied experience, being stuff we can't tangibly touch, but we can observe out in the great beyond, the great unknown, the space in our local galaxy. And tonight we're going to look a little more deeply into astronomical techniques, and particularly SETI, with the meaning the search for extraterrestrial intelligence. And one of the more intriguing observed phenomena out there that falls into the category of something that we've observed, that we can speculate on, is KIC 846-2852, also known as Tabby's star. This star was one of many observed continuously for years by the Kepler Space Observatory, and it was noticed in late 2015 that there was some peculiar dips in its brightness that do not match up to the phenomena we've previously observed. The Kepler Space Observatory is a space observatory launched by NASA to discover Earth-sized exoplanets, or planets orbiting other stars, named after astronomer Johannes Kepler. The spacecraft was launched in March 7, 2009, into an Earth-trailing heliocentric orbit. Now, while these dips in brightness are almost certainly a natural phenomenon, we never like to rule out the idea that strange things might be results of either errors or artificial tinkering of the instruments. So it's been suggested errors of our instruments or artificial tinkerings of actual intelligent life forms on that star. So one of the things that it's been suggested it could be is a mega structure. A Dyson sphere is an example of that. Just exactly what you would imagine. Something so large, artificially constructed, that it could be capable of absorbing and blocking light from a star observed all the way in our solar system. I'm going to be dividing this topic into two parts. Tonight's part, is going to be elaborating on exactly what the Kepler Space Observatory does and has done and has observed, and how it observes, and, well, lots of other ideas about how we interpret that data. And at the very end I will tell you about Tabby's star a little more. And in part 2 we're going to find out, using scientific techniques, or at least being informed by them, what possibilities this observation of a dimming star could mean. So, I guess if you're watching this a day or two after this has come out, then more than likely you'll have part 2 to jump right to if you want to get into the much more speculative aspect of this topic. But I think it's a good idea to have a basic understanding of how our instruments both measure data and how we use these instruments to interpret the data, and how we use rational reasoning, logical arguments, and just look at the facts to try to understand and speculate as little as possible before we reach a more probable conclusion of what this dimming might be. Because as fun as it is to observe, especially out in space, unique phenomena and immediately assume it's aliens, we want to be sure not to do that too quickly. We want to look at the evidence and make sure we've tried to explain it as best we could with known features first. Features of our universe and physics. So, what is the Kepler Observatory? So this was launched in 2009. It doesn't orbit Earth, but actually it trails. It was designed to trail Earth's own orbit around the sun, and getting further and further out. So as it trails, it's going to recede to a much larger diameter in orbital diameter. And of course, the further you get from the sun, the slower your angular velocity is. It's now over 100 million miles away from us. It got further behind us in our orbit because it is a bit further from the sun than us. And the further you're away from a star, the longer it takes to orbit. So the same as being closer to a star or being around a more massive star makes those orbits go a little faster. So which is pretty important to exoplanet finding. But for our purposes right now, it means that Kepler is a long way behind us. Now what this observatory observes is pretty straightforward. It's a photometer, which means it measures brightness. In this case, Kepler constantly measures brightness of roughly 150,000 stars, which sounds like a lot, but is actually only looking at the same patch of sky. It's a very small patch too, only about 1/4% of the night sky. And that chunk is incidentally between Vega and Deneb. You probably know Deneb as the star that makes up the tail of the Cygnus swan. And Vega is the constellation Lyra, both of which are fairly close to the Big and Little Dippers. and the North Star Polaris. In fact, Vega was the North Star for our ancestors about 13,000 years ago, and when the Ice Age was ending. And it's actually a whole nother topic. Oh, I don't have it with me. I was gonna grab my Ancient Egypt book. But there is speculation based on evidence that both the Sphinx and the pyramids of Giza were actually built perhaps much, much further back in time than we or modern Egyptologists currently agree upon. Because the Sphinx is a lion, and as far as we know, the zodiac signs of the constellations have stayed consistent, and the lion is found to be looking at itself, its analog in the night sky. Not now, but about 13,000 years ago, if you use astronomical data and reverse engineer the orbital mechanics of our solar system, what you'll find is that Earth is on a slight wobble, and although it does this at an angle, it rotates on its own axis as it orbits around the sun. If you sped it up and looked at it more like a really fast spinning top, you would find that just like a top, it actually wobbles a little bit like that. And each cycle takes about 26,000 years for it to return to its starting point. But that's all to say that maybe I'll do an episode on that soon. It's very, very fascinating, and it's based on the fact that the Sphinx shows signs of rain weathering, which we all know Egypt is a desert, and the only water it gets is from the life-giving vein of the Nile River. But anyways, that's speculation, which I of course love. But back to our topic about Tabby Star and just how we find other planets. Earth has a 26,000-year planetary precession, and at the moment that makes Polaris the North Star. And Vega will get its turn again, but it's also where terms like the age of Aquarius come from, since the sun appears in the spring equinox of the northern hemisphere in one of the zodiac constellations, and that changes every couple thousand years. And right now it's called Aquarius. So Kepler tilts its eyes up and looks at the patch of sky year-round, and it just watches for any increase or decrease in brightness of those stars in that patch, which is again about 150,000. Many of these stars have other names or catalogs, numbers too, but they exist in the Kepler input catalog, KIC. So that's why Tabby Star is prefaced by that. Kepler wasn't looking for new stars. It was observing known ones. But not many stars actually have names, since there are many of them. So many of them that it isn't unusual for one to have multiple catalog entries. So as far as the naming convention, because there are multiple sets of catalogs, I guess they're called, that aren't always in communication with each other, the the same star can be named multiple things, can have multiple names, if it's being observed by two different groups of either amateur astronomers or actual astronomers. So if there's something interesting found about a star in particular, it's really kind of arbitrary what it's named, but there are a lot of exoplanets, and a lot of them have names beginning with Kepler or Gliese, and then a number in that name just tells you the catalog. The Gliese catalog, for instance, is a catalog of nearby stars, originally published in 1957 by the German astronomer Wilhelm Gliese, and it's been kept up for, and surprisingly a lot, for those stars. Of those stars had no other name. And so this catalog was the first one from which modern astronomers draw from as candidates to look for exoplanets around stars. So you're going to see a lot of Gliese or Kepler for star names, but that's just a convention that happened because scientists are known to be the most creative people, and they are the most efficient, to their credit. So why bother naming a million different astronomers' names when you could just have one or two, and maybe in the future rename it if it becomes particularly exciting and worth revisiting a lot. Maybe only then give it a special name. Yeah, and it's akin to like naming the island Atlas or Rand McNally, because that's what modern atlases are called, or modern atlases are called. That's what books with maps of places are called, and one of the main manufacturers, like one of the main catalogers of stars, was Gliese, is Rand McNally. So just as an analogy. So how do we hunt for exoplanets? Stars dim for many reasons. Ours even fluctuates in brightness, and they all do. But a common cause is from an object getting in the way. And a pretty big object to cause a star, it takes a pretty big object to cause a star to noticeably dim, or at least a pretty close object. For instance, Mercury blocks a lot more light than Mars does, actually, even though it's quite a bit smaller. Now, to detect a planet this way, you need three things. First, you need for its orbital plane to be tilted towards us. In other words, you wouldn't see Mercury. You need it to be in the line of sight. If it's, well, how am I going to do this? If it's orbiting this way, from your perspective, you wouldn't be able to see it because it doesn't traverse in front of the sun. If it was orbiting the poles. So we can't see an exoplanet around a star that's orbital plane is cocked away from us, and that's most of them, honestly, because it's just a crapshoot. People tend to think that solar systems line up with the galactic plane, but they mostly don't actually. Ours is even tilted about 60 degrees off of it, which, 45 is like that, so 60 degrees is even more. Second, you need there to be a planet there that's big enough or close enough to the sun to block enough light for us to notice it. And that's why virtually all the original exoplanets were huge things of size, with, in comparison to Jupiter, a lot of them were even larger. And they were, in fact, even closer to the Sun than Jupiter is, and therefore we called them hot Jupiters. Just mainly being the first things we observed because they were easier to observe. The bigger it is, the more light it blocks, but the closer it is, the more light it blocks as well, and the more likely it is to be between us and that star. A tiny little planet like Pluto far away from the Sun is very unlikely to line up with its star. And an observer is so small and far away, it blocks virtually no light. It also takes a long time to orbit, which is the third thing. You need to stare at these stars for a long time to not only see dimming, but also a repeat of that dimming, because after all this, we're talking about science here, and we need repeatable phenomena, we need evidence, and what am I trying to say? The result of the experiment has to be reproducible. So you want at least 2 or 3 times. Earth would block light, for instance, to an observer from another star system once a year. By definition, Pluto would do it every couple of centuries. And until you've seen this periodic dimming at least a couple times, you can't do much else. Once you've observed it at least twice, preferably thrice, you can take that period and say there's a planet there and it has an orbital, I always say that, an orbital period, I always want to add more syllables, it has an orbital period of so many days, and from that, combined with the star's mass, you can calculate how far it is from its own sun. You can then take that star's brightness and determine if that planet might be close enough to have liquid water on it instead of ice, or far enough away from the sun that it's not boiling and uninhabitable. We call this the Goldilocks or habitable zone. I didn't know what to do with my hands, oh boy. If Earth were around a much more massive star, but at the same distance, our year would be shorter, and we'd also burn to death because there's the fact that more massive stars are more brighter. A star twice as massive as our own isn't twice as bright. It's actually about 10 times as bright. It's not a linear relationship. We also wouldn't be around such a star anyway, since a star twice as massive as our own sun would only have a lifespan of about a little over 1 billion years, where ours is 4.6 billion years old. And the sun was, a good 4 billion years old before animals started emerging. Once we developed beyond mere multicellular organisms, or unicelled organisms. So we don't just look for planets around distant suns. We have, after all, found thousands of them in the last decade. We look for planets in the habitable zone, At least said he does. And Kepler's method, which is just one of the exoplanet hunting methods, is a pretty good one for those types of hunts. If, for instance, we detected a drop of less than a percent in a star's brightness for a day or so, once every 750 days, around the star about half again our sun's mass and about 5 times as bright, we'd know that there was a reasonably Earth-sized planet hanging out about 1.8 astronomical units, or AU, which AU just means the distance from our sun to us. It's about 93 million miles. So this would be 1.8 AU, in other words, is just 1.8 times the distance from us to the sun. And the planet in question would get about half again as much light as we do. In terms of sunlight per unit area, meaning it would be pretty hot, but maybe habitable. We wouldn't much care about one blocking more than a percent of light because it would be too big to be potentially habitable as a planet, and one blocking a lot more than a percent would presumably be huge. We wouldn't much care. Read the same sentence twice, whoops. And by the way, this is kind of a collage. I don't know, it's a document I made based on numerous articles I found on Google, but it was inspired by Isaac Arthur's channel, his episode on Tabby Star. So if I were you guys, I would highly recommend going to check his channel out. It's not quite ASMR, but it's not really that loud, so you could definitely fall asleep to it if you get sick of me talking about it. Indeed, way too huge for even a gas giant if it were orbiting that far out. And when you're collecting data from about 150,000 stars each day for years at a time, you're not looking at that raw data. You have a computer shuffling through it. And it only knows to look for the exact characteristics that you have programmed into it. Alright, so now let's specifically talk about this star, now named Tabby Star after it's got enough recognition and has been revisited enough times to warrant its own unique name. Because it is half again our sun's mass, about 5 times brighter than our sun, as we just said. We've detected this anomaly twice, and a dip in brightness of 15%. So we had a dip in brightness of 15% the first time and 22% the second time we saw it. The first time was in March 2011. The second time was in February of 2013. So a spread of about 750 days. So Kepler launched March 2009. So we just missed the chance to see it then. And the observatory was having a problem in April of 2015. So it appears that Tabby Star is in fact at it again on Friday of this year, 2018, March 16th, Tabitha Boyajian, the astronomer who was responsible for discovering the star's variations in flux. And her colleagues reported that the star was dimming yet again. It's being observed in 2013. Wow, nice. So, we're going to speculate mainly in order to learn what possibilities there are out there, but for now, to probably not be dismissed as pseudoscience scientists, which is probably the worst. Yeah, probably the worst derogatory defamation you can give a real scientist is to call him a quackademic, pseudoscientist, to use John Anthony West's terminology. But nonetheless, NASA, or I think maybe SETI's official statement was that they believe it was just what was the word term? They think it was a dust cloud. Yeah, they just thought it was a big cloud of dust spread out and unevenly distributed, so it was creating uneven clumps. So the dip was huge, but not what was being looked for, since it most definitely wasn't an Earth-sized habitable zone planet. With that period, it would be closer to Venus than Earth. In how much light it gets, it would be a lot bigger than Jupiter. Second bigger dip was also very irregular, dimming then very slightly brightened and dimming way more, something you might expect off a double planet, or coincidental conjunction of two planets at the same time that it was orbiting, if that made sense. So nobody noticed it before the third occasion would have happened, and it was actually volunteers or citizen scientists, as they've been getting called, who poured through the data manually in the Planet Hunters project. And citizen scientist is a new term traditionally called an amateur astronomer. And astronomy has in fact relied on them for a really long time. But regardless, I like the initiative to bring more folks into the hunt. And the fact of crowdsourcing, it's awesome. It's one of the great effects of our globally connected internet era civilization. And it's starting to show up as a genuine alternative to either government or big business research, especially in things like SETI and astronomy in general. I find it, both fascinating and incredibly potentially useful. Anyway, nobody saw it in time for the 2015 dip, or we could have arranged to look at it without Kepler, which was malfunctioning at the time. But once they did send it onto the astronomers, who went, what the fuck? Or, pardon the language, but that was what they said. They nicknamed it the WTF star, but what they proclaimed claimed to mean by that was actually where's the flux, in reference to the weird flux in brightness. Eventually, instead of calling it by its Kepler catalog number, or its technically not a curse word, cognomen, everyone started calling it for the lead author of the team that wrote it up, astronomer Tabitha Boyajian. I'm just going to go with that one. Or Tabby Star. And she's also led the campaign to get funds to observe the star in more detail and in different frequencies than Kepler did. First, as I mentioned, a dip of this magnitude at that distance, a bit under twice as far from the star as Earth is from our sun, 1.8, means that this thing is huge, whatever it is. What does all this tell us? You know, it's much bigger than Jupiter. It's hotter than Earth since it gets about 150 times, or not 150, 1.5 times more sunlight per unit area. Now, I want to mention that Tabby's star is an F3 star, either on the main sequence or in the late stage of what we call a subgiant. It's decently brighter than a main sequence star of its mass should be. Not tons like an actual red giant, but the assumption is this is an old star that's near the end of its life. And that's been challenged more recently, but we'll get to that next episode. Now, for a star of this mass, it would mean creeping up on about 3 billion years. And again, our own sun is about 4.6 billion years. Obviously, we'll be talking about the alien artifact option, which is the megastructures or artificial dimming of the sun in some shape or form. But I want to drive home now that this thing is around a star that's maximum lifetime would have caused it to die right about the same time multicellular organisms were just coming to existence on Earth. And the thing in question is pretty hot compared to Earth. So, all in all, it's not a great candidate. But for alien life. But that's not going to stop us from exploring the more interesting, perhaps, speculations about what it could be in our next episode. So guys, I once again hope you enjoyed this. A lot of you guys really, well, a lot of you are probably here because you saw the Kepler Kardashev scale video. And I'm just really pumped that you guys, somehow it went like semi-viral, for me at least. I only had like, a couple thousand subs less than 2 months ago. But I don't know, I try to listen to the feedback and I try to learn and pick up on what it is you guys, for the most part, are interested in. I know not everybody's interested in history and mythology and religion and philosophy and psychology, and I know these more astronomical, grandiose, cosmological investigations, episodes, speculations can be a lot more suitable for ASMR and sleep. So I'm more than happy and humbled that you guys enjoy it. So we'll definitely continue to make them. But as always, I appreciate your feedback and, of course, your support. You guys are really just encouraging me to keep going, and it's really nice. And 99% of your comments, actually, I'm going to say 99.999, because even those of you who might initially come off as aggressive or disgruntled for whatever reason, I try my best to respond to everybody. And even you guys, maybe you're probably just having a bad day, because you always come around and say, oh, I didn't mean to come off as this or that, and maybe you just initially wrote that because you didn't think I would respond. So, to me, that's really nice. It's encouraging. It's something to look forward to. I really enjoy that we can connect, and I love talking to you guys about this stuff that I spend so much time doing. So briefly, I just want to give a really big thanks to my pledges, I guess they're called. But, I mean, you guys are just supporters. Doesn't matter if you're on Patreon for a month or a continual support. Either way, I really, really appreciate it. It's so awesome that you guys want to give to the channel and help me produce more content like this. So I just want to say thanks to Eric, Antoine, Sean, Kieran. You guys, you believe it or not, you guys make a huge impact on the channel. I want to say thank you to Debbie C, Mark, Matthias, Joshua, Dylan, Alexander, and of course Steve, aka Hardyaka. I appreciate you. Cameron and Ella. You guys are all awesome. Thank you infinitely for your support. Oh man, it just really, really pumps me up, and it makes me want to produce more content. It's just so kindly welcomed, and it's just so kind of you. So it means a lot, guys. It really does. And then lastly, on PayPal, your donations, Tim and Steve, Curran, you guys, thanks again. Jody, Tristan, and Ryan and Sandy. I don't know what else to say other than I'm honored that you guys would take the time and, of course, the money to support the channel. So it just tells me that I'm doing something right, and makes me want to pay attention and be aware and try to improve every time with my content. To the rest of you, thank you for any support you give me, whether it's likes, comments, subscriptions. It all adds up. So, for now, sleep well, and we'll see you in part 2.